Good afternoon, everyone. Welcome to another seminar of our seminars of the astronomy department. Today, I am really honored to present Rubens Machado, our speaker today. Many thanks, Ruben, for accepting this invitation to give a talk here in our cycle of seminars. So I will briefly introduce Rubens. He graduated from IAG-USP and he did his master studies here at IAG. And he got his PhD diploma from both the IAG and also for the Université de Provence in France. And he was a postdoctoral researcher also here at the IAG and also in some institutions in Chile. He's currently a professor at the IAG and he works with simulations of galaxies and clusters. So Ruben, whenever you are ready, you can start.
Thank you. Good afternoon, everyone. So thank you for the invitation. It's a pleasure to give today's seminar. It's an immense pleasure to be back here at IAG after having been away for more than a decade. Left IAG in 2015. The year 2015, according to numerical calculations, was more than 10 years ago, and it's a surprising result. But anyway, very glad to be back. And for today's seminar, I decided not to focus on one specific topic or one specific recent paper. Instead, I thought I would take this opportunity to give a broad overview of the works that we have been doing over the last 10 years approximately. By we, I mean myself, a few collaborators, and mostly the students, the master's students that I supervised in these, during these 9 years in the Federal University in Curitiba. Right, so for the scientific topics, we're on the realm of galaxies and galaxy clusters. So I divided the content here in these 4 themes, which are first simulations of individual galaxies, where we're interested in the internal dynamics and the morphologies of barred galaxies mainly, and then interactions between galaxies. Third, interactions between galaxies and galaxy clusters. These are environmental effects, focused mainly on jellyfish galaxies. And finally, interactions between clusters, mergers of galaxy clusters. But before getting into the content, let me say a brief words about the tools. So for the simulations, for the idealized isolated simulations of galaxies and of clusters, we use mainly Gadget 4, which is a standard tool in the field, and more recently AREPO in some simulations where the resolution of the gas is more important. What's being calculated in these simulations is the dynamics of the stars, dark matter, and gas. So essentially the physics behind these simulations is gravity, hydrodynamics, and star formation, among other processes. And then there are the cosmological simulations. Now, one of the most important examples nowadays is the Illustris TNG suite of simulations. So these are cosmological simulations of structure formation, and we're interested in studying galaxy evolution using the publicly available data from these simulations. So the Illustris TNG simulation was performed with the AREPO code, which implements the hydrodynamics using a moving mesh instead of the usual smooth particle hydrodynamics from Gadget. And there are these 3 versions now with 3 different sizes of boxes. So since the resolution is finite, the large box with 300 megaparsecs on the side is useful for good statistics of the galaxy population, while the smaller box with 50 megaparsecs on the side is useful when you need the resolution of internal dynamics of each galaxy. So for these simulations, we're interested in using the data to understand galaxy evolution. And then the third tool, which is quite important that I should introduce here in the beginning, is the radiative transfer code SCIRT. So this is important to make connections between simulations and observations, because what is being computed in the simulations is not light, it's mass, But generally, we can use the mass of the dark matter, stars and gas to study galaxy evolution in general. But if we need specific comparisons on specific observational filters, then we need to produce mock images, so synthetic images of how the simulated galaxies would be observed in specific bands by specific instruments. So to give a brief overview, what's being calculated inside SCIRT is essentially taking the input, which are essentially the stellar particles of the simulation, and the output is an image, a FITS file, similar to observations, and what's being calculated between this input and this output is essentially assuming that the stars represent stellar populations, the stellar ages and stellar metallicities are known, so SCIRT calculates essentially a spectral energy distribution, which can then be convoluted with specific filter responses. Also, dust is included because it is proportional to even though there is no dust self-consistently within the simulation, there is a proportionality between the mass of dust and the mass of gas, and this is taken into account as the light emitted by these stellar particles crosses the interstellar medium depending on the orientation of the galaxy. So this is going to be useful for some of the results that I'm going to show in a moment. Right, so starting with the topic of isolated galaxies. Here we're focused mainly on barred galaxies, and the first result that I'm going to show was inspired by this paper from one of our collaborators, Karim Menendez Del Mestre, where she measured the properties of a sample of observed barred galaxies in the local universe as a function of wavelength. So essentially measuring the ellipticity and the length of bars in different futures. The main result is essentially that bars look longer and more elliptical towards the bluer filters. So we wanted to know if this is also found within the barred galaxies in the Illustris TNG simulation. So this is a work from Gustavo Gonçalves, who's a master's student currently in Curitiba. So what he did was to take the sample of strongly barred galaxies in Illustris and make maps not only of stellar light, but also the observed, the mock images. So this is one example of a mock image in the Sloan G band compared to the direct stellar mass from the simulation. It's already clear that the star-forming regions are evident in the blue filter, but also there are consequences for the detailed measured shapes and lengths of the bars. So to measure the bars in simulations or in, before I mentioned the bar measurement, so here are the other filters. So the final panel is the stellar mass, and here are the mock images of one simulated galaxy from TNG made to with mocks made in these filters from the ultraviolet here on the left towards the Spitzer infrared and 3.6 microns on the right. So we essentially we measured the lengths and shapes of these bars. So the standard way to measure bar shapes and lengths is to plot an ellipticity profile. When the bar ends, there is a sharp drop in ellipticity. So this is a common definition of the length of the bar, the radius at which the peak ellipticity has dropped by a certain percentage. So this can be done for the stellar mass, which is often the case in simulation studies, but it can also be done for each of the different filters. So this figure perhaps encapsulates the essential result of this paper, which is the ellipticity profile, not only for the stellar mass, which is the black line, but also for the different filters going from the infrared here in orange towards the ultraviolet here in purple. And it's clear in this figure that the ellipticity of the bar increases as we go towards the bluer filters, and as a consequence, the length of the bar also increases. it may seem a little bit out of place that there is one S plus filter here between these. At first, we meant to mimic the same filters that had been used in Karim's observational work, but in the end, it proved useful to include the slow one filters. And then we realized to have more data points, and then we realized that most of the effect happens towards the blue side. What I mean is that if we added more infrared filters, there wasn't much newer information coming from the infrared part, and most of the dependence of this effect was to be found around the blue filter. But since we needed one more data point before the bar became unmeasurable in the ultraviolet, so in the ultraviolet, the stellar bars are hardly measurable. And it just turned out to be convenient that this particular filter was sufficiently blue to enhance the correlation, but not so ultraviolet as to render the bar unmeasurable. So just a small detail that helped. So this process was repeated for the full sample of strongly barred galaxies at redshift 0 in TNG 50. I won't go into very much details, but the point here is that these are the ellipticities in different filters from the infrared towards the ultraviolet as a function of the ellipticity measured in the mass. And the fact that most of the points lie above the identity line means that the bar is always more elliptical when measured in observed MOCs than when measured directly in the mass. And the other panels, they are all the possible combinations of the different filters, always having the bluer filter on the y-axis and the redder filter on the x-axis. And again, since the percentages of points above the identity line are always high, that's the main conclusion. So similar considerations also apply to the bar length. So this is for the bar ellipticity. There's a similar consideration for the bar length, but there we have to separate the sample into star forming and non-star forming. But that's the end. That was the essence of this result. So this was a nice verification that hadn't been measured before. And so we found that the TNG bars also display this very subtle but measurable dependence on wavelength. Now, moving on to the next result using similar tools. Now, this is a separate issue having to do with the long-standing issue of bar fraction as a function of redshift. So the question is, what's the percentage of barred galaxies in the past at high redshift? So essentially here we have recent data from Euclid, which are these black points, and the cosmological simulations in general, in particular here the TNG simulation, overpredicts bars at high redshift. That's the main issue. The cosmological simulations overpredict bars at high redshift. Here we have something similar. The blue points are also the TNG 50 and observational data here at the bottom. The only way to make TNG bars consistent with the observations at high redshift is to disregard the shorter bars, which is shown here in the red line, which makes sense because at high redshift, well, first, the bars were shorter because they were still forming, but more importantly than that, at such high redshifts, the length of the bar is comparable to, or even smaller, than the width of the PSF. So the shorter bars will tend to be undetectable if they exist. So this is the question that we posed. Could we try to reconcile this discrepancy, trying to find if the simulation over predicts stellar bars because of resolution effects, and or if the observations under detect shorter stellar bars, if they do exist. So we did this using now Euclid filters. So here we have two mock images in these two Euclid filters. This is essentially the optical, and this is the infrared. And so this is one example galaxy at redshift 0.5. So at redshift 0.5, there is this specific galaxy that has a bar length of about 2 kiloparsecs. And the question is, this barred galaxy from the TNG cosmological simulation at redshift 0.5, would it be detectable by Euclid at this redshift, given the instrumental properties? And so we produced mocks in these two filters, prepared them in the same way that is used in the Euclid collaboration, and then we tried to detect this bar. So this bar exists and is easily measurable using the stellar mass maps. This is a theoretical thing in the simulation. And then we applied 3 methods to try to recover if this bar would be measurable. So the first method is essentially a machine learning bot trained on the Galaxy Zoo classification, which is the same tool used in the Euclid collaboration. The second method is the ellipse fitting, which works, but is a bit sensitive when the data is not great. And the third method is the Fourier decomposition. The Fourier decomposition is a standard tool to measure bar properties, and it's very sensitive to even mild non-axis symmetries. But none of these methods will work very well when the extent of the bar is 3 pixels across. So this particular bar was borderline detectable by some of the methods, but not all. And what is important here is that this is a 2 kiloparsec bar, and at high redshift, many of the bars, most of the bars, will be shorter and weaker than this case study that we chose to analyze here. So all of these, so this is a plot of bar strength as a function of bar length. So the weak and shorter bars are these red dots here. This star is the example galaxy that I just showed. And so a good fraction of the bars at high redshift would not be detectable because they are too short and too weak. So that's the result so far. Now this work needs to be extended to higher redshifts. This is some preliminary work also by Gustavo, where, so here we're showing the bar fraction, so not for Euclid anymore, but for JWST mocks, and we have the bar fraction as a function of redshift. So for JWST up to redshift 4, which is quite a lot, so the theoretical bar fraction from TNG 50 would be the red line, the observations from JWST would be the green line, and the TNG 50 measured not from the mass, but from the proper JWST filters would be the blue line, but this is a preliminary result, apparently going in the proper direction. There are other ways to take this into consideration. One could focus only on a subsample of low mass galaxies separated from high stellar mass galaxies, or one could impose a fixed cut of only taking into account galaxies that are whose bars are twice as long as the PSF at that redshift. This works as a first approximation, but apparently these detailed measurements in specific filters, taking into account synthetic noise and the response of the instrument, seems to be giving interesting results. Now, changing the subject to a completely different one, so continuing here on the other works on isolated galaxies. One of the other things that we're planning on working on is the nuclear disk. So barred galaxies have a nuclear disk or a nuclear ring where gas is funneled to the central region. There are papers on this topic by Dmitry Gadoch, Camila de Safreitas on the kinematics of the inner region using the timer project. So we were hoping to look into the very inner region of the barred galaxies in these simulations to try to study these kinematic properties, either looking at the kinematics directly, because we already have the velocities in the simulation, of course, or, as is often the case, pretending that we don't, and trying to make mocks that produce spectroscopic information to try to retrieve indirectly the velocity field, treating the simulations as observations. And just to finish this topic, well, there are other issues in classical studies of secular evolution of barred galaxies. This is one of them. For example, the study of boxy peanut bulges. So this is not the issue of spherical classical bulges, but rather these so-called pseudo-bulges for a while that are now understood to be the bar seen side-on. So in strongly barred galaxies, these rectangular or peanut-shaped structures are understood to be the bar. Right, moving on to the next topic, which are interactions between galaxies. Now, these are simulations of one central galaxy being perturbed by a satellite galaxy. So the first topic is about warps, so vertical asymmetries. And so this was the work of a master's student, Andrés Savide, who is currently a PhD student in Porto Alegre. And we decided to study these warped galaxies. So this is the S-type warp. So this is the case where one side of the stellar disk is bent upwards and the other side of the stellar disk is bent downwards. The usual mechanism proposed to explain this is perturbation due to a satellite galaxy. So we simulated several combinations of parameters varying the masses of the perturber and the orbital radius of the perturber, comparing a barred galaxy and a non-barred galaxy. So here we have the different orbital sizes, different masses, and these color maps here are essentially maps of height. So this is the height of the disk. So the red points are above the plane, and the blue points are below the plane. The main result here is that, for some reason, the barred galaxies proved to be more susceptible to warping than the non-barred galaxies. So measuring here the intensity of the warp, the amplitude of the warp, so to speak, the barred galaxy, which is the blue line, always undergoes more intense warping than the equivalent non-barred galaxy. So we characterize this effect. The mechanism for this is not understood. If we were to continue moving forward with this project, one of the speculations would be that perhaps this has something to do with the buckling. The buckling instability is a well-known phenomenon that occurs in the early phases of bar formation. You might have noticed on this previous slide here that there is a moment when the galaxy temporarily loses vertical symmetry. So when the bar is first forming, there is this bending instability that makes the galaxy synagon look like this mustache shape. And this increases the velocity dispersion, the vertical velocity dispersion specifically. Could be. So these are dynamical processes to look into. Yeah. So when the perturber arrives, in the case of the non-barred galaxy, the galaxy is axisymmetric. But if there's a strong bar, maybe it matters a little the orientation of the bar. Yeah. So this is something to be looked into. Now, moving on to the next topic. No, before we move on, this is just a neat side product. This is the evolution of the bar strength as a function of time. So for the low mass perturbers in yellow, the original bar is essentially undisturbed. For the intermediate mass perturbers, the strength of the bar is decreased by about half, but the bar continues to exist, albeit weaker. And for the very high mass perturbers, the bar is completely destroyed. So external perturbations is one of the few methods I'm aware of to dissolve the bar in an isolated, well, no longer isolated galaxy. So moving on to the next topic, this is connected also to a galaxy undergoing perturbation by a satellite. But now, instead of focusing on the effects that the perturber causes on the central galaxy, now it's the complementary approach. These are the effects that the central galaxy causes on the satellite galaxy. In other words, the tidal disruption that destroys the satellite galaxy and leaves behind the stellar streams. This was the work of another master student, Giovanni. And so essentially, this is, this was a preliminary results where we essentially quantified when numerical simulations are actually necessary, because the orbit of a satellite galaxy could be more straightforwardly computed with an analytic potential, or we could compute the disruption of the stellar stream using a fully self-consistent n-body simulation. The calculation of orbits with analytic potential takes seconds, and fully self-consistent n-body simulations take hours or days. So we just wanted to quantify the errors and find which are the configurations in which it is justifiable to use analytic potentials and to within which error, and which are the configurations where n-body simulations are actually necessary because the error would be too large. So anyway, so the orange line is the analytic orbit, and the points are the n-body. Right, and one final topic in the interaction of galaxies. Elliptical galaxies exist. We can also collide elliptical galaxies. So this is a work that we did a couple of years ago to model one specific galaxy that displayed these shells. So these shells are low surface brightness features surrounding certain elliptical galaxies. So quite common, in fact, and also explained by collisions between elliptical galaxies. So these low surface brightness features might be interesting to look at in the near future from LSST data and so forth. Right, so moving on to the next theme, jellyfish galaxies. So here we're focused on the ram pressure stripping. So ram pressure stripping is the well-known phenomenon that takes place when a gas-rich galaxy moves through the gas of the intracluster medium. Because of this wind, the gas loses a sometimes considerable part of its interstellar medium, and this has consequences both in star formation, color, and mainly in depleting the reservoir for future star formation. So these are examples of observed galaxies from the GASP project. Here we're seeing the stars in the optical, and here the gas in H alpha. So we can see, for example, this galaxy presumably is moving towards this direction and leaving a tail of gas behind. So the extreme cases of ram pressure stripping are these galaxies that we call jellyfish galaxies because of the tail that they leave behind. This is a particular configuration that I will mention in a moment. Right, so to simulate these kinds of galaxies, we employ this technique of a wind tunnel. So the idea is to construct a box of gas to emulate the properties of the intracluster medium, the density and the velocity of the gas. So the galaxy is placed stationarily in the center of the box, and it receives a wind comparable to what it would feel in the intracluster medium. These simulations are run with AREPO, and then we can study all sorts of properties of gas loss and star formation, etc. So this was the work of another master student, Elvis Melo Terencio, who's currently starting his PhD at Observatório Nacional. And in this project specifically, we asked the question of what would happen to a jellyfish galaxy if it crossed a sloshing cold front. I haven't introduced the topic of cluster mergers yet, but sloshing is a phenomenon that occurs when a galaxy cluster is perturbed by a collision, and the cool core of the cluster, the cold gas, which was in the cool core of the cluster, is disturbed and gives rise to these large-scale spirals. So this is a spiral in the intracluster medium, and it extends hundreds of kiloparsecs, and it's a spiral of cold, dense gas. The temperature of the gas doesn't matter very much for room pressure topics, but the density does. So when the galaxy crosses this discontinuity and enters a denser gas region, it should be subject to even more intense room pressure stripping than it was before. But this goes into the question of how the population of jellyfish galaxies would compare between relaxed clusters and disturbed clusters, right? Merging clusters. But in fact, what our results showed is that there are measurable effects in the star formation rate and even in the color of these galaxies, but these effects are first small, of the order of maybe 5%, and more importantly, short-lived, because it takes 200 mega years for the galaxy to cross this discontinuity, and so the galaxy quickly resumes its original color and its original star formation rate. So this would point in the direction of concluding that the simulations do not predict that there should be a noticeably different population of jellyfish galaxies in merging clusters when compared to relaxed clusters. As far as I know, this is more or less in line with recent observational conclusions, showing that if these effects exist, they are probably mild and short-lived. I mean, it's not expected to be radically different, the colors of jellyfish galaxies in such clusters. There are no magnetic fields. So, right. Only the normal hydrodynamics. There are works that use magnetic fields in wind tunnels, but as far as I understand, they're not expected to be a major mechanism in this situation. So this is, okay, moving on to the next topic. So this is another way to study room pressure in galaxies. So this is also room pressure, but in a configuration where the galaxy is receiving the wind not face on, but receiving the wind edge on. So the result is not to develop a tail perpendicular to the stellar disk, but rather to unwind the spiral arms of the stellar disk. This is a known morphology. Now we saw an example in the observations, and curiously, this sort of thing appears in the simulations, now whether you're looking for it or not. So we did some preliminary work in this direction, trying to quantify the shapes and the amount of unwinding of the spiral arms. I mean, room pressure is a gas. It's a hydrodynamic phenomenon, right? It's gas on gas. So the room pressure cannot unwind the stellar arms directly. But once the gas in the spiral arms is sufficiently disturbed, then, well, this gas will form new stars and they will not be axisymmetric anymore. So this can also be quantified. This is a quick example of a simulation. We're looking at the gas density. This is a galaxy falling towards the core of a galaxy cluster. This is a wasteful simulation. It's hard to justify simulating a megaparsec cubed of gas if we're interested in room pressure in just this galaxy, but it's one possibility to make a self-consistent simulation. And then the gas unwinds, as we saw in the right panel. Maybe I'll skip this one in the interest of time. Okay, very quickly. This is the U-warp phenomenon. It's a different kind of warp where where all sides of the galactic disk are bent on the same direction. But what is peculiar in this morphology? So this exists. There are galaxies that display U-warps, and the explanation for this phenomenon is also room pressure. What is unexpected here is that the bending of the stellar disk, and not the gas. The stellar disk is bent forward, which is a bit peculiar. The gas tail is, of course, towards the back, but the stellar disk, the edges of the stellar disk are bent forward. And apparently, the explanation for this is that it's not that the edges of the stellar disk were pushed forward. It was the center of the galaxy that was pushed backwards, because the run pressure stripping is proportional to the density, where there is more gas densities in the center, so the center undergoes intense run pressure continually, and it ends up moving the center of mass, so to speak, of the galaxy backwards a little bit. This is a very small effect, but measurable. So anyway, meant to conclude this soon. We're also looking at star formation in the tails of jellyfish galaxies. This is the work of a master student there in Curitiba, Nicolas Schweder Souza. And star formation in the tails of jellyfish galaxies is particularly interesting because this is one of the very rare occasions in the universe where you have star formation outside of a galaxy, right? So, I mean, stars outside of a galaxy are not unusual. This is what intracluster light is. But in the case of intracluster light, it is understood that these are stars that were already formed within galaxies and then were stripped by normal tidal and gravitational interactions. But here, the stars are being formed in the gas outside of the galaxy. Of course, these stars are not being formed from the intracluster gas. Obviously not, because the intracluster gas is extremely low density and extremely hot. So what happens is that these stars are being formed, well, in clumps, dense clumps of gas that are now outside of the galaxy. So somebody might claim that, well, it's not really outside, it's just a small chunk of the interstellar medium that happens to be outside of the galaxy now. But then it's not interstellar anymore, and then maybe it's the outer stellar medium. So this is something to be looked at. And finally, to conclude, there are jellyfish galaxies that appear spontaneously within the TNG simulation. And we're now trying to characterize the properties of these jellyfish galaxies, particularly at large radii, 3, 5 Virgo radii from the center of the cluster, going towards the scale of filaments, measuring the distance of these jellyfishes to the filaments. This is work by Richard Albuquerque. So we're collaborating now with Claudia, Angela, to try to connect this to S+ observations. So the other part of this project is to try to make observational mocks of the jellyfish galaxies in TNG in the S+ filters for comparisons. This is also work by Gustavo. Still on the topic of jellyfishes, we started something a couple of years ago to try to use the simulations to find a way to determine the direction of the trail vectors of jellyfish galaxies. So the idea here was basically to take simulated jellyfish galaxies, project them at random angles, use this to train a neural network to identify the directions in another separate sample, but this is very preliminary. Maybe we should retake this in the future. This one I'll skip and move on to the final. No, tá bom, very quickly. This is not our work, but perhaps a more interesting way to distinguish between, to look at asymmetric galaxies and distinguish if the asymmetry is caused by tidal interactions or by run pressure stripping, which is extremely not obvious, just from looking at the observed images. So there is this method introduced by Rory Smith last year, where they use simulations. So it's a very nice method, and they measure and they try to find some sort of signature in the simulations that would indicate whether the galaxy is asymmetric due to run pressure or to tidal interactions. And it turns out that it has to do with stellar ages, because in the cases of tidal interactions, there is no reason to be any segregation of stellar ages. Now, both sides of the galaxy are stretched more or less the same. But in the case of run pressure, the side of the galaxy that is facing the wind gets compressed. That's why there's more star formation on this side, because the gas is denser. And now you have more younger stars on this side of the galaxy than on the other side of the galaxy. And this more or less works for different inclinations. So we were thinking that we could maybe, but this is just a preliminary idea, but if we could get stellar age, but the problem of this method requires stellar ages. If we could get stellar ages from, someone can correct me later, but from some version of starlight applied to S+ data, then maybe this method would be applicable. Or complementary, we could use, again, the simulated galaxies from TNG, where we already have the stellar ages, or again, we could pretend not to have the stellar ages, use the TNG mocks in the S+ filters, try to recover the ages, and see if this method is applicable, because there we know the correct answer. Anyway, it's just a preliminary project for the future. And now to conclude with the last theme, which are mergers of galaxy clusters. So this is a line of research that I started with Gaston around 2011. I won't go into details of all of the clusters, but the general idea here is to model collisions of galaxy clusters, to model specific merging clusters using data from weak lensing, which gives us essentially the mass maps, and using data from using X-ray data, because the gas of the intercluster medium is often perturbed in such collisions. And then we can use these simulations to, so to speak, reconstruct the dynamical history of the merger and find out what are the mass ratio, the age of the collision, and so forth. So we applied this structure to a long list of merging clusters, which was the work of several students, some of which are now PhD students or postdocs here at IAG. I won't go into the details of this, but let me just mention 2 or 3 types of topics of interest in this field. So, for example, there are some collisions where the collision is dissociative, in the sense that the dark matter becomes dissociated from the gas. This is the well-known case of the famous bullet cluster. There are several other examples of dissociating clusters nowadays where we can study separately the dark matter and the gas. So this on itself is an interesting topic. There are situations that are mentioned that develop the sloshing spiral, which is quite common also in observed clusters. We can study the Mach number of the supersonic collisions that are often, almost always supersonic in such collisions, and so forth. There's an argument to be made whether the limits of this approach are being reached. One possible extension in this topic would be to maybe include radio, to calculate the emission in radio relics, because there's radio data for a lot of clusters nowadays. But in any case, I would argue that this type of tailored modeling is still necessary and useful to understand the observations, to interpret the observations. So just by looking at the morphology of temperature maps and X-ray maps, it's often quite uncertain to speculate about the dynamics of these systems, because the experience of these simulations shows that the dynamics is often quite non-intuitive. So this is still a useful tool to model individual clusters of interest and to help interpret the observations. But perhaps the more recent frontier in this field might be in the TNG cluster simulations. So TNG cluster is a new version of the TNG simulations with a much larger box of 1 gigaparsec. So at least the cluster regions within this 1 gigaparsec box are resimulated at high resolution. And the main point of this is that now, and this is very recent, the data has been made available last year, now we have proper statistics for clusters and cluster mergers in particular. Before TNG cluster, there simply were not enough massive clusters within such a small cosmological volume to allow for proper statistics. And now we have hundreds of clusters of 10 to the 14, 10 to the 15 solar masses. And so there's a lot to be done there. We can study the shock fronts. We can use this pool of realistic cluster mergers to search for analogs to specific observed merging clusters. And there's one specific technical detail that I've been meaning to do, which is to take one of these very massive textbook, binary collisions of two galaxy clusters from TNG cluster, find its parents at a slightly larger redshift, and use this as the initial conditions to recreate an idealized version that we're used to simulating, and then finally quantifying the amplitude of the errors because of the simplicity of the binary collision. So in these idealized collisions, the clusters are spheric, there's no substructure, there's no magnetic fields, etc. And so the question is how, after all, do they compare to the more realistic cosmological environment of a TNG cluster? Right, so this is a promising field. Okay, so here I finished the content. Let me just show one final slide to mention that if everything goes according to plan, I was hoping to organize a short 3-day workshop in July to teach these techniques to the new students, basically focused on these 3 skills here. How to run simulations of galaxies, how to access and analyze data from cosmological simulations, and even how to produce observational mocks, even though this last part might be too specialized. But in any case, the idea, if all goes well, of this workshop would be to have sort of general lectures in the morning, followed by hands-on computer activities in the afternoon. So this might be interesting for students. And I'll leave the link to my page here where you can find the videos of the simulations and other materials. And I'll stop here. Thank you.
Thank you very much, Rubens, for your great talk. So let's start with questions.
Hi, Rubens. My question is regarding the fraction of bars that you presented, a redshift 4 snapshot. As I remember correctly, there are around 400 galaxies in that snapshot, which is not that much. So it seems that I don't know if you did or somebody else did, but I didn't see any paper being cited in that card.
No, the observations are not ours. But it's quite possible. I suspect that the number of galaxies is very small. Not only. This?
Yeah, no, the previous one. Yeah, that's one.
That maybe I shouldn't have shown this. This is very preliminary, but this data should have been. Wait here. Well, anyway, the high redshift data from JWST should have been taken from a recent observational paper. I won't know the exact number of galaxies, but I trust that there are probably very few.
Well, that's the thing, because we have been doing this morphological classification at high redshift. And even using Illustris data, a redshift higher than 2.5, you don't know for sure if the galaxies are disk or spheroid dominated, which means you have no way of saying if there are bars. On top of this, these people, they use visual determination if the bar is present, which is really pretty bad. There are other ways of measuring bars, but it's very difficult to find bars, especially at high redshift. So people are basically thinking, those methods they use at the low redshift and applying to the high redshift, which is, to me, it seems very wrong, and it's no surprise that the error bar that you present there is enormous.
No, I agree. This is surely, the highest redshift beam is surely the most uncertain, for sure. Probably the Euclid data, which is limited to redshift about 1, will be more robust, probably more reliable. But you're right, the number of galaxies is small, not only in the observations, but also in the simulation. So that the fractions from the simulations are also from small number galaxies.
Hi, Rubens. Congratulations for the seminar. I have a question about hum pressure stripping outside, very far away from galaxy clusters. Did you look at the environment where the hum pressure occurs? Is it galaxies falling into filaments? What is happening?
That's exactly the point. Now, this is preliminary work, but this is precisely what we find, that these jellyfish galaxies at large cluster-centric radii, they exist, they're there, but they're not apparently, that's not concluded yet, but apparently they're not embedded in the general ICM of the cluster, which would be extremely low density at such radii. They are, most of them apparently, within groups. So they're probably undergoing run pressure, not because of the global surrounding environment, but because they are embedded in the intra-group gas of where they live.
Oh, okay, so they are in groups.
Apparently.
They are not isolated.
Yeah.
Okay, thank you.
Oh, hello. Great talk. I working with the interaction between the stellar bars and jellyfish galaxies, the evolution. So the all topics for me was very interesting. I hope I have several questions, but first one is how in the first topic do you talk about the length of the bars and different wavelengths? How you measure the length of the bar and blue wavelengths? Because not all galaxies or barred galaxies have information in the blue wave galaxies. No, for example, the strong barred galaxies are red. No, we don't have information in. Well, maybe yes, I don't know, but usually we found clones of the star formation in the ends of the bar, but only in that regions. And when you measure the length of the bar, but not only measure the ends, but not along the bar, and
yeah. So these properties of the bars, they are all measured using ellipse fitting. So in principle, it takes into account all of the light between one isophote and the next isophote. So this is done for some filters in this relatively small sample of observed galaxies, up to apparently the B band. But it's true that towards the blue and even more strongly in the ultraviolet, then they become essentially unmeasurable. So there are not enough young stars emitting in the blue or in the ultraviolet to even allow the bar to be measured, at least in these filters. But towards the normal bluer...
For the galaxies, have a weak bar or strong bar? For the galaxies?
Well, that's a good point. This entire work was done using only the bars that were classified as strongly barred in TNG 50.
Only strongly barred?
Yeah.
Okay. Another question is about the environment cause destroy the bar. What are the conditions in order to destroy the bar? Because some other simulation says the interaction could be incentive the formation of the bar and become more strongly the bar. So I would like to know what is the condition to some perturbation or galaxy destroy the bar.
Well, it's a merger, né? I mean,
merger.
In those cases, yeah.
Okay,
So the satellite galaxy starts at an original orbital radius, but spirals in and is cannibalized by the main galaxy.
The satellite galaxy have the similar stellar mass, or is a small galaxy?
Much smaller, much smaller.
Smaller.
So, like I showed there, 0.1, 0.5, and 1, 10 to the 10 solar masses, compared to a disk of 10 to the 11 solar masses, I suppose.
Oh, okay.
So,
the central galaxy have a strong bar?
In those simulations, yes.
Yes.
Particularly strong because we were focused on the differences between barred and non-barred, so the barred was a particularly strong bar. that was either weakened or destroyed in the extreme cases due to a merger.
Okay. Well, thanks so much.
Okay. We don't have more questions. Yeah, we have. Sorry, I didn't see.
Rubens, regarding jellyfish versus tidal interactions. Okay, jellyfish galaxies are a result essentially of run pressure winds, right? Run pressure is rho v squared of the gas, density times the square of the velocity of the gas, so it's related to gas properties, right? While the tidal interactions are dominated by gravity. So an interesting way to distinguish between the two samples or studying the two samples is it would be to look at the gas properties, gas and magnetic field properties as well in one case, right, jellyfish, and magnetic field properties as well. Why? Because when you have run pressure, you have compression of the gas, and the compression itself raises the amplitude of the magnetic field strength and therefore of the magnetic pressure, so that magnetic pressure and thermal pressure will be of the same order, so they will be both dynamically important in the evolution of the ram pressure effects and the jellyfish tail formation, right? So locally, even though globally magnetic fields do not matter, locally in these local phenomena, it may matter a lot because it will it may drive the evolution of these tails as well, right?
I see.
So in one sense, do you believe that considering the gas properties, looking into the gas properties of the jellyfish galaxies, and on the other hand, looking into the other sample that where tidal interactions should dominate, you'd then look at the stellar properties more, would be a way to distinguish between these two samples?
I see. No, that's a good point. The gas is probably a good source for information in this regard. I suspect that what you mentioned would be relatively easy to access in the simulations,
exactly.
Because
and
then we have all
the observations as well.
Yeah, and for the observations, I mean, then I guess it would depend what data is available for the sample, right. If limited to the optical or not.
Okay. Can I make another quick question? I suppose that jellyfish galaxies are more frequent in high redshifts, right? Because you might have more interactions, and so my question is there a study of the distribution of high redshift galaxies? I mean, is there an idea of the difference between the amount, the distribution, the frequency of events in high redshifts? You know, not high redshift, but high enough, those that can be reached.
I don't have a specific result to quote right now, but I would speculate that since galaxies were more gas-rich in the past, I suspect they would be more prone to...
closer and denser in the fact that you might have more interactions.
Yeah, also true.
Because the cosmological simulations do predict this, so I was wondering if the observations, IAG-USP observations, have already some statistics of, that is comparable to what is predicted from the TNG simulations and the other cosmological simulations.
No, that's a good point. I would have to look into that.
Okay. Thank you.
Yeah.
Okay, so let's thank the speaker again, and you are all welcome to discuss with Rubens during the coffee break. Thank you.